Hello guys, welcome to the second lecture of sets in the series of lectures of sets. So in last lecture we learnt about types of representations, types of way to represent a set, and we learnt about that there are two forms. First is the roster form and the second is called set builder form. And with our experience with some examples, we got to know that set builder form is more precise and is a more elegant way to represent a set. So let's take one more example and and let us recap what we learned in the last lecture. Okay, so for example, let S be a set of all rational numbers. Okay, so in set builder form we can represent it as P by Q, and we can put some conditions on P, and we can define P that P belongs to integers, P belongs to integer, and Q belongs to natural numbers. So that's another way to represent all rationals. So I think that's the most important thing we learned in the first lecture. Now let's continue the second lecture. Okay, now let's begin this lecture with some remarks which we learned in first lecture. So the first remark is a set may contain another set. Example, this set contains all natural numbers, all integers, and all complex numbers. So a set may contain another set, and it is also true that a set may contain itself. Second remark is a repetition of element makes no difference. Okay, so these two are the same sets because one is repeated here, so it makes no difference at all, because the definition of set actually defines or actually validates the possibility for these sets to be equal. Okay, and the definition of set was unordered collection of well-defined objects. And the third is ordered does not matter. So in a set you write element in 1 2 3 if the elements are in the order 1 2 3 or in the order 3 to 1, it does not matter. Both sets are equal, because again the definition itself validates the existence of these two equal sets. Okay, now we'll learn about some of the more fundamental things that are related to sets, that are often called as properties of a set. Okay, so let's jump there. Now among the properties, the first thing what we have to learn is order of a set. Now what is order of a set? So if let's say there is a set S, then what will be its order? So order is actually defined as number of elements in the set. Okay, so if S is a set that is defined as 1 2 3 and 4, then order is represented with the notation that's called n of S. That's the order of set S, and that is equals to 4, that is number of elements. So order is number of elements in the set. Okay, so this is very and we can take one more example. So as we described all even natural numbers, so in set builder form we can define even natural numbers as n, where n belongs to natural numbers and 2 divides n. And if I ask, and if this is kind of set, let's say this is set A, then what is n of A? So of course that would be infinite, because there are infinite numbers that are even and they are natural numbers. Okay, so that's the order of set. Now we'll talk about equal sets. Okay, so two sets are equal. For example, let's say that there is a set A or let me write it more concise. So set A and set B are equal if all elements of A are elements of B. We can take example that if we define A as this 1, 2, 3 and 4, and we define B as 1, 2, 4 and 3, then we can say that A equals to B. But, and if you take, let's say, another example where let's say set P is defined as 1, 2, 3 and Q is 1, 2, 3 and 4. Obviously we can see that this 4 is not in this guy, so P not equal to Q. So that's about equal sets, and now we'll learn about equivalent sets. Okay, so let's learn about equivalent set. So let's learn about equivalent set. So let's talk about set A. If set A is 1, 2, 3 and 4, and set B is 4, 1, 3, 2, again we can say that order does not matter in a set, as we learned. So these two sets are equivalent. A and B are equivalent because the elements are same. If I can write this as, let's say, if I add another 4, again they are equivalent because elements are same. All the elements are same, therefore they are equivalent. Okay, now we'll learn about another property that's called the power of a set. Okay, that is very important. Power of a set is a very important property in sets, so let's learn about that. So let's talk about power of a set. So power of a set is actually defined as a set containing all the subsets of any set. So if there is a set, let's say, if I explain this with the help of an example, let's consider this example. S is 1 and 2. Then power set would be defined as, and it is represented by the notation P of S. This means power of set S, and it is defined as another set that contains all the subsets. So this contains all the subsets. So this contains 5. Null set is also a subset. This contains 1. 1 is also a subset of S. It contains 2. 2 is also subset of S, and it contains 1 and 2. 1 and 2 are also subset of S because a set also contains itself. So this is power of set. A set containing all the subsets of any set is called power of a set. So that's all about that. Now we'll learn about one more very important property, and that's called and that's the called algebra of sets. So let's go there. Now let's talk about a very basic thing, but a pretty tricky thing, and that's about null set. So what is a null set? Null set is represented by this. This means null set, or we can simply represent by a symbol, a Greek letter phi. This is null set. So the question is this a null set or not? Is this a null set or not? The answer is no. Why? Because it is not a null set. It is a set that contains a null set. Null set is this, and the set that contains a null set is not a null set. Okay, actually this is place where definition of numbers was actually introduced while being in contentious relations of David Hilbert and Henry Poincaré. We will talk about that later, but a question was asked in in mathematics at that time, that what is infinity. But so there was a mathematician who said that forget about infinity, what is number 1, what is 2. So numbers were defined like this. So numbers was defined like as so they thought that what is a number. So a number 0 is an empty set, number 1 is an empty set containing an empty set, and number 2 is another empty set containing an empty set which contains another empty set. Okay, so that's how number were defined. So, and it can be intuitively thought as 0 is an empty bag, number 1 is an empty bag which contains an empty bag, number 2 is an empty bag which has an empty bag which still has an empty bag. So that's how number was defined by using set theory. And by this example you could imagine that how proficient and how important set theory is in the field of higher mathematics.